Here we go. Let's do a little bit of monkey type. Not bad. One again. Nice. All right. Do another tree. Binary tree from pre-order and in-order traversal. You're given two integer arrays, pre-order and in-order. Is the pre-order traversal of a binary tree. In-order is the in-order traversal of the same tree. Both arrays are of the same size and consist of unique values. Rebuild the binary tree from the pre-order and in-order traversals and return its root. The pre-order 1, 2, 3, 4, 1, 2, 3, 4. In order, I would expect this to be 2, 1, 2, 1, 3, 4. And you build the tree. The pre-order 1, in order 1, returns 1. Root. Okay, so the idea is in pre-order traversal, you're gonna have the action like here. And in order traversal is where the action is here. I guess what can I say to that? When you build the tree, you might need to, have some node, tree node, some value is equal to some value. Everything else is none. And then this node might just be added to the prev, maybe, of left. Or, prev right node. Obviously if it satisfies a condition. But the thing is, how would you want to build this? When you do this in a pre-order or in order, doesn't matter if you use one or the other, do you have to use both? Pre-order could be I guess you could think of it as some global I variable starts at 0. You do the DFS. For something. If node tree val I don't see why you wouldn't just use the pre-order to build this tree val only. I guess you wouldn't know where to place, say, the 4 if you only used pre-order, because there's null values, and you think, okay, when you have an in order, you'll also be able to identify which side it is on. So in order helps to identify which side it is on. If you just use in order, you wouldn't know which is the root node. So you wouldn't know where a node stems from. So you would maybe use this is a tree problem. Maybe pre-order, 1 has to be the root. 2 has to be the left and 3 has to be the right. No, you might not know that. Two is the left. I mean, 2 could be the right. 3 could be the right and 4 could be the right. In order, tells us, okay, 2 is on the left of 1, and 3 is on the right of 1. So pre-order, you get 1, you find 1 in order, and you say the left and right will be the left and right nodes of 1. And then you look at 2 in pre-order, well, that's already satisfied. 3 already satisfied. 4 not visited. So does 4 go Can you guarantee it's 3 and not on 2? Pre-order means it'll have to be you have to do 3 before you can do 4. So you can just go to 4 directly, and then in order, can it be on the left or right? Is that a question? Okay. Let's have a look. TFS binary tree. Okay, before looking at the solution further, can 4 be on the left of the 3 and not on the right of the 3? Is there any way to identify that? Yep, the 4 would have to be before the 3. Otherwise it would be after the 3. And pre-order would be 1, 2, 3, 4. In order is 2, 1, 3, 4. When you look at that 1. When you reach the 3, you don't necessarily want to pass on it. The 2's parent is going to be 1. It's not like and 3's parent is going to be 1. Pre-order, you look at 1, say, okay, left is going to be 2, right is going to be 3. Okay, now let's go to 2. The left of 2, there's nothing. The right of 2, there's nothing. So you would say okay. Let's have a look here. If not pre-order and not in order, or not in order, return none. Valid. But the root is equal to the tree node where the value is the pre-order 0. Yep. So this is done recursively. Then the mid is to find the index of the pre-order and you would build tree for the pre-order 1 to mid plus 1. And in order to mid. Interesting. You're breaking this down into sub-problems.
Hey everyone, welcome back, and let's write some more Leetcode today. So today let's solve a pretty fun problem. Construct a binary tree from a pre-order and in-order traversal. So we're actually given two integer arrays representing 1, the pre-order traversal, and 2, the in-order traversal of a binary tree. And our goal is to take these two traversals and the orderings of those nodes and then reconstruct basically the original binary tree that the traversals are from. And it is technically possible. These two traversals have all the information we need. We just need to take that information and then deconstruct it and then reconstruct this binary tree from those. So just to verify it, let's go through this tree and actually do the pre-order traversal first of all. So first, we know pre-order traversal is you start at the root and then you process the current node, then you do the left subtree, then you do the right subtree, right? So let's just do the pre-order traversal. So we're starting at the root. We do the root node first. That's how pre-order works. So then we get a 3. Next, we're going to go to the left subtree and then do pre-order traversal on that left subtree. We see 9, right? So we're going to add 9 to our pre-order traversal, and it doesn't have any children, so we're actually done with 9. We're done with 3. Now it's time to do the right subtree in pre-order traversal. So we start at 20, add 20 to our pre-order, go left, we see 15, add 15.
Copy multi. Hi David, how are you going today? Good. Tired though. I've been at uni. Now I'm back though.
15 to the pre-order. 15 doesn't have any children. Now we go to the right subtree, 7. So add 7. It's our last node. to the pre-order traversal, right? And this actually, take a look at this, take a look at all the values. It matches exactly with the input. So this is the pre-order traversal. Now let's just validate the in-order traversal as well. In-order traversal is we start at the root, right? We take care of the entire left subtree first, then we take care of the root node, and then we take care of the right subtree with in-order traversal. That's the general order, so let's validate the in-order traversal of this tree. So we're starting at 1, we're starting at the root 3, but we're not going to add 3 yet. First, we're going to do the left subtree. We see we have a 9. The 9 does not have any left or right children, so now we can add that 9 to our in-order traversal. Remember, we're doing this in order, left to right. We go back up to the root. Now we can process the root. We can take 3 and add it to the in-order traversal. And now we're going to do the entire right subtree. So we get to 20, but we're going to wait for 20. We're going to first do the left subtree, 15. 15 is the only value here, so it doesn't have any children. Add 15 to the in-order traversal. Now we can add 20 because we've done the left subtree. 20 is added, and then last we go to the right subtree, only one value, 7. Let's add that 7 to our in-order traversal. Now let's take a look at these 5 values. Notice how they are the exact same 5 values in the exact same order as that in-order traversal that we were given. So we can see that what they gave us was correct, but now the question remains, how can we actually take these two arrays, these two traversals, and construct this tree? Well, it's definitely possible. Let me show you how to do that right now. So I just want to let you know that there's actually two main facts that we're going to be using to construct this tree. So the first fact is that the first value in pre-order traversal is always going to be the root, right? We remember when we do pre-order traversal, right? We're always processing the root first. So if I was taking the pre-order traversal that we're given, right, we remember this is the pre-order traversal that we're given. The first value in pre-order traversal is always going to be the root. So this is the first value, 3. It's guaranteed to be the root because that's how pre-order traversal works. The first value in pre-order traversal is always the root node. Now we don't know about the rest of these, right? But we can recursively construct now the left subtree and the right subtree, right? We're done with this 3, right? Now our goal is to reconstruct the left subtree. Hey, lucky for us, the first value here is always going to be the root of the left subtree, right? Because that's how pre-order traversal works, right? So that's one thing that we're going to use. The first value is always going to be the root, and then we can take the sublist, right? We can remove the 3. We don't need to look at it anymore. Then we take the sublist, and then basically we're going to do this recursively. That's what I'm telling you. Okay, we can construct the root, but we need more information than that, right? And then let's say we're done looking at this 3 now. I want to take this array, right? And I want to know which values are going to go in the left subtree and which are going to go in the right subtree. From looking at the actual tree itself, we know the answer, right? We know that this is where we're going to cut our list, right? The 9 is going in the left subtree, right? These 3 values are going in the right subtree. But how can we determine that? Well, that's what we need our in-order traversal array for. Okay, so now let's take a look at the input array we're given for the in-order traversal. And by the way, let me just mention that every value in the traversal is guaranteed to be unique. That's true for both of the traversals, the in-order and the pre-order. Every value is going to be unique because every value in the tree is going to be unique. But okay, so far we know that this first value 3 is going to be the root, right? So now let's find 3, right? We know 3 is the root, right? So we removed it from our first list basically, right? But now let's find it in our in-order list. We find it's right over here. 3 is in this index, right? So we know we don't need this 3 anymore, right? We already created that node. But so now what does this in-order array tell us? notice how this is convenient for us. Every value to the left of the 3 that we just created the root from, every value over here, which is only 9, is going to go in the left subtree, and every value to the right of 3 is going to go in the right subtree. That's really convenient for us. Why is this the case? Because that's basically the purpose of in-order traversal, right? It guarantees that we're going to go through the tree in order, right? From left to right, basically, right? So if we see the 3 here, and this is the position in the array, we know everything here is going to be in the left subtree, everything here is going to be in the right subtree. That's what it tells us. This is really convenient for us because we can count it, right? We can see there's exactly 1 value that's going to go in the left subtree, and there's exactly 3 values that are going to go in the right subtree. So what we can do is we can take the remainder of the pre-order array and then partition it, right? Partition it over here because we know 1 value is going to go in the left subtree and 3 values are going to go in the right subtree. So that's what we're doing, and we're going to continue this, right? So now let's and by the way, in the code, we're going to do this recursively. Let's create the left subtree. We know that, okay, this is the in-order portion, right? And this is how we're going to partition it from pre-order, right? We see this is the array to create the left subtree. The thing here is, notice how this is size 1, right? There's only 1 value here and there's only 1 value here, right? That tells us that the subtree we're creating is only going to have 1 node in it, right? So 9 is the only node in the left subtree. So we're going to create that node, put the value there, and now we're basically done with this left subtree, obviously, because there's no more there's no more nodes left in this general area, right? These values are reserved for the right subtree. This is reserved for the right subtree. Okay, so now we're looking at the pre-order portion, right? There's 3 values, just like in the in-order portion. And remember, how are we going to create the root node of this subtree? Now, we always take the first value in pre-order traversal. It's 20, right? The value is 20. So we're going to take this value 20. We don't need it anymore because we're going to create a node from that value. And so now we need to know which values are going to go in the left subtree and which are going to go in the right subtree. We know by finding 20, right? 20 is the value. Let's find 20 in our in-order traversal. It's over here. By the way, in the code, I'm going to be calling the index of this mid. So M for mid. We find the index of 20, right? We know we don't need 20 anymore, so we can get rid of it, right? We see that there's 1 value on the left of 20, and there's 1 value on the right of 20. This tells us that 1 value is going to go in the left subtree and 1 value is going to go in the right subtree, right? Just like we have over here. So now let's construct that left subtree. We know it's going to be exactly size 1 from looking over here. So we take this 15, right? Now our job is to recursively create the left subtree.
I get it.
We're going to take this 15 since it's the first value in the subarray for pre-order, right? We know that it's going to be the root of the current subtree we're at. So let's get rid of this 15. Let's create that node, right? 15 over here is going to be a node. And there's no more values left in this subtree because we know it's only going to be size 1. Okay, now we're creating the right subtree. We know that there's only 1 value in the right subtree from looking over here. And since there's only 1 value left in general, it's a 7. We can make a node from it, and then we're done. We know we're done because we've basically gotten rid of every single value in our arrays, pre-order and in order. So using these 2 arrays, we were able to create our tree correctly. And let me summarize what we're actually doing. We're not doing a lot. We don't need a ton of information. Remember, the first value in pre-order, the pre-order array is always going to be the root, right? That's just how it works. And then once we take that value, create a node from it, and then when we try to look that value up in order traversal, right? Then we can get some subarrays, right? We can take we can take the length of the left and right subarray. So the right subarray is 3 and the left subarray is 1 node. Now these counts 1 and 3, they tell us how to partition the pre-order traversal. So take a look at the pre-order traversal. 1 tells us that we're going to cut over here because this needs to be size 1, this needs to be size 3. And then from this subarray with only 1 value, we are going to recursively run the algorithm to create this left subtree. And with this subarray, we're going to recursively run the algorithm to create this subtree. And we're just going to continuously repeat that process until we get to our base cases and until we're finished with every single node that we need to create. So now let me actually show you the code. It's actually
what's the base case? That if it's equal to empty list or in order is equal to empty list, you return zero, nothing. At the end of the day, you want to return the root. So you return none if there's no pre-order or in order. The root here is equal to pre-order, return root. Perhaps, yeah, you just return none. At this point, you're guaranteed to have some value in the pre-order, so you can index it by 0. Now he uses a mid, he says, which how am I going to do this? He's going to find the mid of the in order at index of the root value. So we shouldn't call this root, but just some value, right? Maybe just call a root val. Because the root is going to equal to tree node of val equal to root val. The mid is where you know to partition by. In the pre-order. Has to be mid plus 1, right? And and up to pre-order of mid. Self-build tree, pre-order, and then something in order. In order is just the you get rid of 2 and you get rid of 1. And your in order is just going to be the left. Reorder, that is going to be no, I'm taking it off this, the in order. So in order should be this, I think. But pre-order, you remove 1, and you're left with 2, 3, and 4. I'm not getting it entirely. We make the root this. Mid is in order of the root val. root left is equal to self-build tree. Okay. In order mid, self root right, build tree, pre-order, and in order. So the pre-order is correct. But you go from 1 to mid plus 1. Because... Right, because you know where it's going to be split. There's also another one that I got to redo at some point. Alright, we'll put this as a solution. (105) Construct binary tree from pre-order in order to traversal. There's an even more efficient solution. Okay. I wonder if it's because you use a different language. So maybe C++. So you don't necessarily use a DFS something something. It's more understanding why you would use it. It's a concept that I'll have to revisit in time. But it's good. Maybe we just watch the last bit
Hey
of
everyone,
this.
welcome back. So now let me actually show you the code. It's actually very short, less than 10 lines. Okay, so as I mentioned, this is a recursive algorithm. So we always want to start with the base case, and the base case is going to be, what if we don't have any nodes to traverse through the two arrays that we're given? That means we can return null, or basically we don't have to create a tree. So if pre-order is empty or in order is empty, then we can return null. We have no values, so we don't need to create a tree. We can return null. Otherwise, we're going to create a tree node, right? And what's the value of that tree node going to be? Well, it's going to be the first value that happens to be in the pre-order array, just like I showed you, right? Always going to be the first value, so it's always going to be index of 0. And then whatever that value was, we want to find the position of it in the in-order array. So in-order.index, so we want the index of that value, pre-order of 0, and we're going to get it in mid. Now this is the part where we're going to build the subtree. So root.left, let's create the left subtree, and we're going to do this recursively as I mentioned. So self.build tree, we're calling the function that we're inside of. And the convenient part about Python is we can do sublists, so that's going to cut down our code quite a bit. So we need to pass in the new pre-order and in-order arrays, or the subarrays more likely. So pre-order, what are we going to pass in for the left subtree of pre-order? Well, mid tells us how many nodes we want. The index of basically the value of mid tells us how many nodes we want in the left subtree. So what I'm going to do is, for pre-order, we're going to start at index 1. We're basically skipping the 0 index because we already just created a node for the 0 index. We're starting at index 1, going all the way up until mid plus 1. In Python, this mid plus 1 is non-inclusive, so this subarray is really just a pre-order from index 1 to mid. So that's what we're doing, and we're going to pass in the in-order portion that we need as well, and that's just going to be from the beginning up until mid, but not including mid, right? This probably makes more sense if you go back and look at the picture, but basically we're just creating the appropriate sublists that we need to create the left subtree. We're going to do basically the exact same thing with the right subtree. And I would encourage you to draw this out yourself to basically reinforce what you're learning or watching me do right now. So to build the right subtree, we need every value after this sublist, right? So we can just say starting at index mid plus 1, going until the end of the list. That's how you do it in Python. We're starting at mid plus 1 and going until the end of that sublist, just like I showed in the picture. And for in order, we can actually do the exact same thing. We want every node to the right of mid in order, right? From our in order array, we want every value to the right of this index mid. So we can do that with mid plus 1, starting at mid plus 1, and then going until the end of the array. So now let me close this function. And so this is literally all you have to do. The reason it's so easy is mainly because I'm using Python, but you could do this code without Python. It would probably just be a couple extra lines. You might need to pass in a couple extra parameters into this build tree function, basically just these indices that I'm doing. You might not be able to create sublists, but you can at least pass these indices into your functions in Java and other languages. So with that, we have actually created our tree, so the only thing left for us to do is return that tree. So with that being said, this is the final solution. It's probably less code than you would have predicted, but the problem is a little tricky, but it's kind of enjoyable, at least in my opinion. So I hope that this was helpful. If you enjoyed
This is, man. Annoyingly, time consuming. For each pixel in the image, im0, gotta stand. For each pixel in the image, disparity 0. J offset, which is just a column left and right shift offset. For each pixel in the image, move the pixel to a new position . Offset the pixel in the horizontal axis . as specified by the disparity map. So the ground truth disparity map to warp M0 to move the pixels to where they should be for M1. Holy shit, I just realized, you know, there's so much shit to do. Because I'm thinking of tomorrow as well now. The stuff that I gotta get done. And this assignment is just one of the many. Wow. God damn. Am I right to say... Yeah, we have 2 weeks more. Yeah, I say I want to have a working MCTS as a soft deadline. Oh, that is, yeah, that is hard to say. I don't think it's worth thinking about at the moment, so I'm gonna have to push this deadline a week. It's not, I don't like the idea of pushing it like this. In the final submission, by the way, we haven't even properly considered this for this subject, this specific one. But APA, I don't think this is the correct panel. Maybe it is actually, never mind. Maybe it is the correct panel. Okay. So if you think about it, this is the right image. This is the left image. You print the right image with the remapped left image. And the left image is obviously going to include some less details. So the left image has to be warped, I guess, sideways. And some black lines that you can see here might be because of, you know, when you look at it from the right image down to the left image, down to the object, your right eye would see it wider than your left eye would see the object. So a brief explanation on how the image warping code works, why the result of image warping has lots of black pixels, e.g. to the right of the backpack. Okay, so for each pixel in the image, offset the pixel in the horizontal axis as specified by the ground truth disparity map. And the thing that I should try to understand is, you know, what these offset values are. So I suppose I should run everything up until this point. Why is the result of warping? Ooh. Interesting. I'm gonna see this in a scrollable element. Okay, there's more that's just getting removed. Instead of a scrollable element, how can I now undo that? Open in text editor. I guess after, oh, right, okay. Fine as is. Yeah, it's just a growing list, okay. And do these differ? They do. But they are all still just, yeah, they're still all positive numbers. You know, can we assert okay, I know it's a tensor. So J offset, is what I kind of need to understand. Close this. Perhaps we should call the stream an end so that my computer doesn't kill itself. Alright, we'll call it an end to the stream for now. But I'm going to be doing this offline just because it's easier. It'll probably save some headache. Alright. Thank you for the one person in this stream. Catch you later.